Good afternoon, esteemed colleagues. It is an honor to be here at the 5th International Conference on Educational Technology and Online Learning. My name is Volodymyr Yuzichov. Today, I will be presenting our work titled Mathematical Support of Adaptive Learning based on a fuzzy non-deterministic automaton and a graph representation of educational content. This research is the result of a collaborative effort by a team of authors, Professor Tunke Sevendik, Professor Iyer Shubin, Hanna Plahova, and myself. Within the framework of today's presentation, we will examine the key problems of modern distance education, propose a methodological approach to their resolution based on a comprehensive mathematical apparatus, and discuss the scientific and practical results of our research, as well as the prospects for its further development. Proceeding to the substance of the matter, it should be noted that current trends in the development of distance learning present a series of complex challenges. Traditional approaches, oriented towards the static delivery of information, prove to be ineffective under conditions of rapid technological progress and the growing need for individualization of the educational process. Within our research, we identified two key, interconnected problems. The first is the problem of integrating heterogeneous content and the absence of unified standards. Today, we are observing an exponential growth in the volume of educational materials. These include online courses, video lectures, and interactive simulations. All are presented in diverse formats, which significantly complicates their consolidation into a single digital ecosystem. The absence of unified standards leads to information fragmentation, the incompatibility of educational platforms, and, consequently, to a substantial decrease in the overall effectiveness of the educational process. The second fundamental problem is the acute need for profound personalization of learning. Standard, one-size-fits-all approaches do not account for the individual characteristics of each student, their current level of preparation, preferred learning style, and personal cognitive attributes. In this regard, there is a pressing need for the development of adaptive mechanisms capable of analyzing student performance in real time and automatically adjusting their educational trajectory. Thus, the scientific and practical task that we set forth in this work is the resolution of these complex and multifaceted problems. We assert that their solution requires the development of new methodological approaches and instrumental tools for the creation of a truly flexible, interactive, and adaptive educational environment, which constitutes the primary objective of this research. Based on the outlined problematic, we have formulated the main aim of our work. It consists in the development of mathematical software for the creation of Universal Learning Management Support Components, or LMSC. These components are intended to become integral parts of an intelligent adaptive system designed for the effective integration of heterogeneous educational and methodological materials. To achieve this aim, we propose a specific approach and a mechanism for its implementation. The foundation is the representation of all educational material in the form of a directed graph. In this structure, the nodes are specialized didactic units, slides, and the edges are controlled transitions between them. A key feature is that the transitions between slides are not static. They are selected dynamically, based on data about the specific student and the current state of their learning. This allows the system to react promptly to their results and instantaneously adjust the educational process. The application of such an approach enables us to achieve three key objectives. 1. To implement a profound individual approach, allowing the system to adapt to the needs and characteristics of each student. 2. To determine the most effective strategy and tactics of learning for each individual case. 3. And finally, to provide real-time learning with the capability for rapid response to any changes, which minimizes deviations from the optimal educational trajectory. Now, let us consider in greater detail how exactly we propose to structure the educational material. As previously mentioned, the foundation is the organization of the course in the form of a graph, the nodes of which are slides. We distinguish between two types of slides: informational slides, which contain theoretical material in the form of text, graphics, audio, or video; interactive slides, which additionally contain test items to facilitate feedback. It is these that serve as branching points in our graph, as each such slide has at least two outputs: task completed successfully and task completed unsuccessfully. To evaluate the results on interactive slides, we employ a binomial model of a pedagogical test, where the outcome is assessed on a binary scale: 1 for success, 0 for failure. This approach allows us to mathematically substantiate the necessary number of test items to achieve the required precision and reliability of the assessment. As you can see on the slide, the number of items n depends on a series of key parameters: the probability of successful completion p, the reliability d, and the precision epsilon of determining the true score. For instance, to determine a true score of p equals 0.6 with a precision of 0.1 and a reliability of 0.8, it is sufficient to prepare 40 interactive slides. This allows for the substantiation of the volume of its assessment part in advance, at the course design stage. We now proceed to the core of our system, the individual student model. In a distance learning environment, the instructor lacks the opportunity to intuitively assess the state of the learning subject, as occurs during in-person contact. To bridge this gap, we propose to consider learning as a human-machine system and introduce a formalized model intended to emulate this assessment process. This model is constructed based on the expert assessments of the instructor and the continuous analysis of data on student performance. For the mathematical description of this complex and multifaceted entity, we have selected the apparatus of automata theory, specifically a fuzzy non-deterministic automaton. Its formal definition, A, is displayed on the slide. The choice of this particular type of automaton is predicated on the fact that the learning process is inherently fuzzy and non-deterministic. A student's answers are not always absolutely correct or incorrect, and their decisions are not always deterministic. This model allows us to translate the complex pedagogical process into the rigorous language of mathematics, thereby creating a foundation for subsequent computations and the construction of an adaptive trajectory. Now, let us examine how the abstract model of the automaton acquires a concrete, operational form. The expert knowledge of the instructor, embedded in the transition function delta, is represented as a set of fuzzy transition matrices T, as reflected in Formula 2. In practice, this means that for each learning method U, a distinct matrix is created, indicating the effectiveness of transitioning from one state to another. Thus, the system operates with an entire library of rules. For a conceptual understanding of the learning process, however, a fuzzy graph G, described in Formula 3, is far more suitable. The nodes of the graph are the student states X, and the edges are the transitions between them. It is fuzzy because each edge has its own weight or degree of membership mu, which is derived directly from our transition matrices. To definitively link this model to reality, we interpret its components as follows. X sub I represents the results of the IH test, Y sub j represents the time intervals for learning, and L represents the payoffs or value associated with the implementation of a particular learning method. This dual structure provides us with both the computational power for analysis and a clear visual representation for constructing learning trajectories. On this slide, we will examine the key mechanism of our work: how a static expert model is transformed into a dynamic and individual one. The first step in this process is the construction of an individualized transition function. We utilize input information directly from the student, their own forecast regarding the preferred learning methods for achieving a particular result. Next, a synthesis of expert knowledge and individual preferences occurs. At each step of the learning process, the model adapts by solving a system of compositional equations, presented in Formula 4. These equations allow for the computation of a personalized fuzzy assessment of the possibility of success by integrating objective data from the instructor and subjective data from the student. Following this, the system must compare the objective possibility of success with the student's subjective choice. For this, the choice consistency condition, shown in Formula 5, is used. The expression mu of x sub I given u sub L functions as a validation criterion. The subjective assessment of the preference for a learning method mu of u sub L should not exceed the objective assessment of the possibility of achieving the result mu of x sub I given u sub L. If this condition is not met, it serves as a signal for the system that intervention is necessary. It is this mechanism that allows for the identification of the most robust and probable connections between test results and learning methods for each student individually. Now that we have an individualized model, we can utilize it to search for and select the optimal learning path. This slide is dedicated to how the system defines and formally describes learning trajectories or strategies. To find the optimal route, we employ the dynamic programming approach. The system proceeds not from the beginning to the end, but in reverse, from the final goal back to the beginning, evaluating the effectiveness of possible transitions at each step. The quality assessment of one such transition, alpha, is calculated using Formula 6. It considers both the student's own preferences and the objective value or payoff from this action. After evaluating the individual steps, we formally describe the entire path using Formula 7. A strategy, in our understanding, is a weighted path on the graph, which is represented as a sequence of states and applied learning methods. Next, we must define the value of the final outcome. For this, the concept of a fuzzy goal is introduced, described by Formula 8. This function assigns to each possible final result a degree of its value for the student. Finally, having the assessments of all steps and the value of the goal, we compute an integral assessment for the entire strategy, beta, using Formula 9. The minimum operation is used here, which implements the principle that the quality of a strategy is determined by the quality of its least effective component. A strategy will receive a high score only if each of its steps is acceptable, and it leads to a valuable result. On this slide, we arrive at the culmination of our model, the resolution of one of the fundamental problems in pedagogy. The essence of it is that the strategy subjectively preferred by the learner is not always the most objectively effective for achieving the educational goal. Our model formalizes this contradiction of choice using two criteria. Formula 10 performs a search for the strategy that maximally corresponds to the student's style, that is, has the maximum assessment beta. At the same time, Formula 11 searches for the strategy that leads to the best possible goal, that is, to the result with the maximum value mu. The solution to this contradiction is the transformation of strategies. If the system determines that the path chosen by the student is ineffective, it initiates a change, proposing a transition to a mixed strategy. To determine the moment for intervention, we introduce the concept of the coefficient of freedom of choice. It is calculated as the ratio of the number of admissible strategies, those whose assessment beta is above a given threshold epsilon, to their total number. If this coefficient becomes too low, it serves as a critical signal for the system that intervention is necessary. Based on this, we formulate 3 tasks for the system. 1. To recommend to the student steps that are part of admissible strategies. 2. To transform the strategy if no effective paths remain. 3. And to reprogram the model when conditions change, for instance, the student's preferences. In conclusion, I would like to formulate the main findings and results of our work. The main scientific result is that we have developed a comprehensive mathematical apparatus based on fuzzy logic and an automaton graph model. This apparatus allows for the formalization of the student model, effective operation with uncertainty, and subjective assessments, and the management of complex dynamic aspects of individual learning. The practical significance of the work is manifested in two key aspects. Firstly, the proposed graph-based approach contributes to solving the problem of standardization by offering a unified method for representing heterogeneous materials. Secondly, our methodology lays the foundation for the creation of intelligent tutors, systems capable of proactively constructing and adjusting personal learning paths in real time. And the overall conclusion is as follows: the proposed approach, which combines content structuring and deep personality modeling, lays a solid scientific foundation for the creation of a new generation of educational systems, truly personalized, flexible, and highly effective, which, in turn, will contribute to enhancing the quality and accessibility of education in the modern information society. On that note, I would like to conclude my presentation. Thank you all for your time and attention. I would also like to express my gratitude to the organizers of the iStall conference for this wonderful opportunity to share our research.